All right, so this is our video on graphing a polynomial function. So as a reminder, a function that contains only operations of addition, subtraction, and multiplication, that's no division, integer exponents are considered repeated multiplication, is a polynomial function. So polynomials have smooth turns and are continuous. Also, when you're looking at a polynomial function, it has real coefficients and integer exponents. Right? The shape of a polynomial is affected by its degree and the sign of the leading coefficient. Oops, spelled coefficient, right? So this will tell us what our end behavior is too. The degree and the leading coefficient tell us our end behavior, meaning what the ends of the graph look like. So also remember, when simplified a polynomial function, the variable x can be written in this format. So that is in standard form, that's highest degree to lowest degree. This is also called expanded form. N is a positive integer called the degree, and each coefficient is a real number. So multiplicity, zeros. Let's talk about what those things are. So we know zeros of a polynomial function. We can find them. So let me fast forward here. Is anything? Here we go. Okay. So this right here, this polynomial function is in factored form. And we can find the zeros or the x-intercepts by setting each factor equal to 0 and solve. We could also tell what the multiplicity of each of these factors are. So if you look at our first factor, x plus 3, it has a multiplicity of 1. If you look at our second factor of x minus 1, it has a multiplicity of 2 because that factor appears twice. Because of that, we can tell if the graph crosses or bounces off the x-axis. If the function has an odd multiplicity, like this one, it's going to cross through the x-axis at that 0. If it has an even multiplicity like this, then it is going to bounce off the x-axis or touch the x-axis. That's what this says right here. So multiplicity is the factor of f, Sorry, let me read that again. If x minus r to the m power is a factor of f, then r has a multiplicity of m. So notice the 0 has a multiplicity of m. Right? Zeros can have even multiplicity or odd. If it is an even multiplicity, it will bounce or touch the x-axis, however you want to say it. And then if it has an odd multiplicity, it will cross through the x-axis. Okay, so even, it's going to bounce off of it because it's keeping the sign. Remember, it's staying positive or staying negative. And then if it's odd, it's going to cross through the x-axis. So I already mentioned end behavior, so let's talk about end behavior here. So when we're writing end behavior, it's going, okay, there we go. It's going to look like this, right? So the first one is left end behavior. It's as x approaches negative infinity, what is happening to the function. So basically what this is saying right here, as you look left on your graph, is the function pointed upward or downward? That's what you're answering there. If there's an arrow pointing upward, it's positive infinity. If there's an arrow pointing downward, it's negative infinity. Okay, so to determine what's happening to the graph, we are going to use the degree and the lead coefficient. So there's 4 different options of what you can have, okay? We can have the degree be even. So we'll put even in both of these. Or the degree can be odd. Put odd in both of those. And then the lead coefficient can be positive or negative. So the lead coefficient will do even and positive, even and negative, odd positive, odd negative. So it's different combinations of those. All right, so let's talk about what happens with each one. So let's do a sketch of a graph or a possible, what are we talking about here, right? So if the degree of the polynomial is even, so the highest exponent is even, and the lead coefficient is positive. So let's give ourselves an example of that. Let's use y equals instead of f of x just to keep it simple. Positive lead coefficient, so let's do 1. And then an even degree, let's do 2. So y equals 1x squared, or just y equals x squared. We know what that looks like. It's a parabola facing upward. So if we fill in this, is x approaches negative infinity. So as you look left, you see that there's an arrow pointing upward. So our function is approaching positive infinity. And then this one says as x approaches positive infinity, which means look right, what's happening to the function? Upward arrow again, so positive infinity. All right, so that is if the degree is even and the lead coefficient is positive. All right, if the degree is even and the lead coefficient is negative, so that's like having y equals negative 1x squared, it would just look like this. We would have, as you look left, there's an arrow pointing down, so that's negative infinity. As you look right, there's an arrow pointing down, so that's negative infinity. So if we summarize that from even degrees, okay, an even degree, if you look at the ends of this graph here, ends, the arrows are pointing in the same direction, right? So think about it as like if I said, you know what, we're even. You punched me in the arm, so I kicked you in the leg, right? So we are even. We have the same results, right? Like, okay, that made no sense, but we are the same. We're even, okay? We don't have to get back at each other. All right, positive, negative, if you look, they're both pointing upward for positive. They're both pointing downward for negative, all right? So lead coefficient, both upward for positive, both downward for negative. I'm still like thinking about my terrible example of kicking and punching and you're the same. That's not the same. Like if you punch me in the arm and I punch you in the arm, right? Then we're even, which is we did the same thing to each other. That's a much better example, even though it involves violence. All right, let's talk about odd degree. Okay, so let's think of an odd degree function. So let's do y equals positive x, positively coefficients. Let's do 1 again. And let's do x cubed instead of just x to the first power, because I want you to actually see the degree there of 3 instead of being like, oh yeah, there's nothing there, but it's 1. All right, so we know what that looks like. It looks like this, right? As x approaches negative infinity, that's going downwards, that's negative infinity. As x approaches positive infinity, as you look to the right, that's going upwards, that's positive infinity, okay? And then for our example of an odd degree, we'll do x cubed again. Negative lead coefficient, we'll do -1, so we have y equals negative x cubed, which looks like this. So as you look left, upward, as you look right, downward. So this is positive infinity, negative infinity. All right, so how can we summarize this? If the degree is odd, the arrows are pointing in opposite directions. Odd, opposite. Even, same, right? Odd, opposite. If it's a positive lead coefficient, it's like if I were to straighten this, it's like a positive slope line, right? If it's a negative lead coefficient, if I were to straighten this, it's like a negative slope line. All right, so let's see if we can do end behavior for these 6 right here. So to determine the end behavior of the polynomial function. So this is straightforward. This is just making sure you understood what I was saying. This says as you look left, there's an arrow pointing up, so that's positive infinity. As you look right, there's an arrow pointing down, so that's negative infinity. Next, as you look left, arrow pointing up. As you look right, arrow pointing up. This is positive infinity and positive infinity. This one, as you look left, arrow pointing down. As you look right, arrow pointing up. So this is negative infinity, positive infinity. Okay, next are from equations. So what we're going to do is we're going to use the leading term test. So we have to make sure it's in standard form, and then whatever the first term is, we use that, okay? The first equation here is in standard form, is expanded out, and it goes highest exponent to lowest exponent. So we are going to look at the first term. If you look at the degree is even, okay? And if you look here, this is negative. So it's even, which is the same direction, right? Even is the same direction. And then negative would be both downward facing. So a sketch of what this looks like is this. Obviously, there's more happening in the middle there, but we just care about the ends. So as you look left, arrow pointing downward, negative infinity. As you look right, arrow pointing downward, negative infinity. All right, looking at the next one, it's not in standard form. It's expanded, but it's not written from highest exponent to lowest exponent. So I would say do that, but if you look, you can just grab it. All right, so if you look here, the degree is odd, right? So my arrows are going to be pointing in opposite directions. And my lead coefficient is negative, so that would be like a negative slope line like this. So obviously there's different things happening in the middle here, but the ends look like that. So as you look left, there's an arrow pointing upward, that's positive infinity. As you look right, there's an arrow pointing downward, that's negative infinity. All right, last one right here. It's not written in standard form, so I could quickly rewrite it in standard form, but I'm just gonna grab my first term, which is this 8x, positive 8x. The degree is 1, which is odd, so my arrows are pointing in opposite directions. It's positive, so it's going to be like a positive slope line. And not just like a positive slope line, this is a positive slope line. As you look left, there's an arrow pointing downwards, that's negative infinity. As you look right, there's an arrow pointing upwards, that's positive infinity. Okay, so now what we're going to do is we're going to bring all the information that we know now and sketch a graph of what a polynomial function looks like, okay? So first off, we need the degree and the lead coefficient so we can describe the end behavior. That's what we're using for this. So if you look at what the degree is, I can't just look at it and see. We did practice with this in yesterday's notes, but it has to be in standard form. I could take the time to do x plus 3 times x plus minus 1 times x minus 1 and multiply that all out to get in the standard form, but I only need the first term. So what I'm going to do is I'm going to multiply all of my first terms. This is x to the first power. And this would end up being x to the second power. So x to the first power times x to the second power is x to the third power. So if you look here, my degree is 3, my leading coefficient is 1. All right, now I can get my end behavior. Your end behavior is always going to look like this. As x approaches negative infinity, comma, f of x approaches, and then you're filling in the blank there, okay? Or y approaches. This one's y, so let's do y. Let's be accurate here. And then for this, and then you're going to have as x approaches positive infinity, y approaches, and you're filling in the blank right there. All right, so we need to know what the ends of our graph looks like. So if the degree is 3, this is odd, and the lead coefficient is 1, this is positive. So odd would be opposite directions, positive would be like a positive slope line. So that's what my ends look like. As I look left, there's going to be an arrow pointing downwards, that's negative infinity. As you look right, there's an arrow pointing upwards, that's positive infinity. Next, number of real zeros. Remember that matches the degree, which is 3, so at most we'll have 3 real zeros. Your y-intercept is always 0 comma something, so we have to plug in 0 for x and see what we get for y. So we'll do x is 0, y is 3 times negative 1 squared, so that is 3. X-intercepts, set each factor equal to 0 and solve. So I'm going to set this factor and this factor equal to 0 and solve. We get x equals negative 3 and these are the x-intercepts, so they're ordered pairs. So we have negative 3, 0, because x equals negative 3. Might as well write that down for my 0. X equals negative 3. And x equals 1 for my other 0. And so my other y-intercept is 1, 0. All right. Also in this section right here, it says zeros, the multiplicity, and whether it's even or odd. So let's look at how many times the factor appears. This appears once, so that's odd. This appears twice, so this is even. And then it also asks, does it cross or touch? So this is the thing that we learned, relearned today. If it's odd, it's going to cross the x-axis there. If it's even, it's going to touch or bounce off. Number of turning points is always 1 less than the degree, so 2. And it's at most, it can happen less than that. All right, so now we're going to sketch what this graph looks like. So we're going to graph our y-intercept. There is no tick marks for your y-intercept, so we're going to add them. 1, 2, 3. Make your y-intercept right there. Make your x-intercepts negative 3, 0, and 1, 0. And then we are going to use our end behavior to sketch what this looks like. So we're going to start with a downward facing arrow. When we get to our first 0 of negative 3, we are going to cross the x-axis. We're going to go through the y-intercept, okay? Then when we get to our second 0, which is 1, we are going to touch or bounce off that, the x-axis. So this is what our graph looks like. Okay, and it's just a rough sketch. It could, if I go back here, I could say that it goes up higher than that and then comes through this, right? And then, whoa, goes like that, let go, and then comes back down. If I want it to look like that, that's fine too, okay? Because it is a sketch. All right, let's try one more here. This, once again, is not in standard form, so let's multiply out. X to the third times x to the first times x to the first is x to the 5th power. So my degree is 5, my lead coefficient is 1. Describe the end behavior. As x approaches negative infinity, this is y once again, so y approaches something. As x approaches positive infinity, y approaches something. So this is an odd degree, right? It's a 5th power, so opposite directions. And then lead coefficient's positive, so just like the other one, it's gonna look like this. So we're gonna say as we look left, the arrow is pointing down, so that's negative infinity. As we look right, the arrow is pointing up, so that's positive infinity. At most, this will have 5 real zeros. The y-intercept is always 0 comma something, so let's plug in 0 and see what we get. So we have 0 plus 4 is 4, 4 cubed. 0 minus 1 is negative 1 to the 1st power. 0 minus 3 is negative 3, and then to the 1st power. 64 times negative 1 times negative 3. We have to do a little mental math here. That's positive. And then 64 times 3 is 192. And then your x-intercepts, zeros. So I'll do zeros first. Set each factor equal to 0 and solve. So I have x equals negative 4, x equals positive 1, x equals negative 4, x equals positive 1, and x equals 3. So that's negative 4, 0, 1, 0, and 3, 0. Multiplicity, this is odd, 1 and 1. So odd, odd, odd. I'm just going to go like this, odd. So I'm going to cross every single time. At most, since there's a degree of 5, this will have 4 turning points at most. Okay, so to sketch this, I need the y-intercept of 192. That's why the y-axis isn't labeled here, so I'm going to put 192 like right there. So I know that this is 0, 192. And then negative 4, 1, 2, 3, 4 right there. 1, 0, and 3, 0. Okay, I'm ready to sketch this. It says start with a downward facing arrow. And then I'm going to cross every time. So I'm going to go through this. I have to hit my y-intercept. Oops, I don't want it to look like a straight line there. There you go. Cross, cross, and end up. Let me make that like that. It's going to end up facing up or arrow pointing up like we said it would. All right, that is all for today. Go ahead and try some practice on your own.